Our focus up until this point has been to look at essentially plain carbon steels, but it turns out that there are abundance of different compositions and an abundance of different materials. One of the really high strength materials that are fabricated from steels is an alloy that's referred to as 4340. And we're going to take a look at it simply because it represents a difference, because there's a change in the alloy composition. There are other elements that have been added. And what we see is as we begin to add other alloying elements, the phase boundaries begin to change, or the boundaries of the start and finish begin to change. So we'll look at 4340 and examine the isothermal transformation diagram for that particular material. We see that we have the regions that we normally do. We have an austenite range. We have an austenite ferrite range where we're forming pro-eutectoids. So we are obviously at a composition which is no longer eutectoid. So we have that AF field. And then we go beyond that, and what we're going to wind up seeing is the formation of pearlite in that next region. And so when all of the austenite is transformed, we find ourselves in the region that is ferrite plus pearlite. So we'll go through these different regions of the diagram and describe what's going on. So generally the way these diagrams are set up, they're set up so that the A represents the austenite, the F is the ferrite phase that forms as a pro-eutectoid, and the pearlite is given here as P. Sometimes what a number of diagrams contain, rather than using P, they will actually just use ferrite plus cementite, and they will take those two ferrites and put them together, and you'll just have ferrite plus cementite. But the reality of it is, whenever you form pro-eutectoid ferrite, you will have ferrite from that decomposition as well as ferrite that forms from the pearlite two-phase microstructure. Now when we go down to low temperature, what we begin to see is the A plus B range. And again, the A plus B range tells us that we have austenite plus bainite, and you can see that dotted blue line, and that dotted blue line represents the 50% line for the bainite structure. When you get all the way over to the solid black line and you're in the B range, that's where the bainite is. When we go down to lower temperatures, what we see is a 10%, 50%, and 90% lines, and those represent the transformations for the development of martensite. Now, what's interesting is, one of the things that's important about adding a number of these alloying elements is that the high temperature phases that are diffusion controlled tend to be pushed to slightly longer periods of time. Ultimately, that's going to lead to materials that are not quite so quench sensitive. And we'll see more about that when we get into actually cooling curves. But we shift that curve slightly to the right in comparison to eutectoids and off-eutectoid alloys. And so those processes are delayed with respect to the eutectoid compositions or plain carbon steels. The other thing that happens is you see a clear delineation between the region in which you form pearlite as opposed to the region where you form bainite. So those regions become physically separated, and you would expect they would because they are actually formed by different kinds of mechanisms with respect to the pearlite forming as a result of the motion of iron and carbon along the austenite-pearlite interface and the precipitation of cementite out of the ferrite when we are forming the development of bainite. So they are different, and we're not too surprised then that we see these transformation curves that are shifted. In addition, when you add alloying elements, with the exception of maybe cobalt, generally what happens is as you add other alloying elements like carbon and chromium and nickel and other elements, what you find is the martensite start and finish temperatures begin to depress. So these diagrams are different, and each alloy will have its own isothermal diagram that has been determined by investigators over the years. Thank you.